Welcome. My name is Gaiman Yee. I'm the Technical Director of the I4 Energy Center. I want to also give a word of welcome to those that are viewing today's seminar via the internet. Today's speaker is Wendy L. Muqad. She is from the California Public Utilities Commission, where she is a utilities electric engineer in the energy division. She has been with the CPUC for over 10 years, ever since the California energy crisis in 2001. She is currently working in the area of electric grid modernization, otherwise known as smart grid, for the grid planning and reliability section. Wendy has a wide array of experience conducting technical, economic, and policy analysis of natural gas and electric energy regulatory issues. She is very involved in smart grid-related standards development and participates in standards-setting organizations such as NIST, IEEE, and IEC. At NIST, Wendy represents the CPUC as a participating state regulatory voting member of the Smart Grid Interoperability Panel. Prior to the CPUC, she worked at the U.S. General Services Administration in San Francisco and the U.S. Naval Electronic System Engineering Command in Vallejo. Wendy is a registered professional electrical engineer in California. She has a BS degree in electrical and computer engineering from UC Davis, and she was a UC Regents Scholar. Let's welcome Wendy.
Good afternoon. I want to say that I'm really honored and humbled to be here today. UC Berkeley is the alma mater of my grandmother, and I brought her picture here. And my great-great-grandfather, he graduated in the class of 1878, and this cup was given to him because he was the first in his class to have a child, my grandmother's mother. So I brought these two things to show my connection to UC Berkeley. Also, I'm really happy to be speaking virtually to the other three other UC campuses, including my own alma mater, UC Davis. So thank you so much for coming. We're going to talk about electric grid modernization and how you can help make a smarter grid. First, I just want to put up a slide about the California Public Utilities Commission, who we are. We're headquartered in San Francisco. Some more information about us, that we regulate telecommunications, electric, natural gas, water, railroad, rail transit, and other companies. The things that we're responsible for: ensuring that customers have safe, reliable, and utility service at reasonable rates. And there are 5 commissioners, and their pictures are here, and they're appointed by the governor, and they're confirmed by the state senate, and they're the ones that make the policy decisions at the CPUC. So I also have a disclaimer, and basically it's just that my presentation is going to give some of my own professional and personal views, so they may not necessarily represent the position of the CPUC. So as you know, the title of my speech is Electric Grid Modernization, How You Can Help Make a Smarter Grid. Initially, when I was asked to speak, I thought of the title based on a workshop that I organized and hosted and facilitated through the IEEE Power and Energy Society in October. And that workshop was Electric Grid Modernization, Current Standards Development, and Cybersecurity Work. In that workshop flyer, we stated that California is embarking on an effort to modernize its electric grid in order to support many of California's overall energy policies, and the importance of current standards development and cybersecurity work in order to achieve California's goals should not be underestimated. Thankfully, my recent work allowed me to get connected with, I'm going to just blank this out so you don't have to watch that while I'm talking about something else. It allowed me to get connected with with a lot of people that are very knowledgeable in the field. I had at the workshop Dr. Jerry Fitzpatrick from the National Institute of Standards and Technology, who's very involved in synchrophaser research. Joe Hughes, Francis Cleveland, and Irfan Ibrahim. And if anyone's interested, we have some great information available, publicly available from that workshop. It was a one-day workshop on our IEEE PES San Francisco chapter website. So when I started thinking about what I would want to talk about today in the short time that I would have to tell you how you could help make a smarter grid, I realized what came back to me over and over and over was I needed to focus on what I feel like is really most needed in our industry, which is more engineering students focusing on power systems engineering. And also, I also feel that it would be great for UC to get involved in this effort more. Let me turn this back on. This is a picture of the North American electric grid, and I wanted to show it because really there are 3 grids in North America. There's a Western grid, there's an Eastern grid, and there's Texas. That's the way it works in our country. So anything that happens in the Western grid, it's really one power system. Everything that goes on in that grid is one power system. And that's what I really wanted you to kind of get a feel for, and why modernizing the grid can be extremely complex when you're dealing with this large of an infrastructure. This is some things about the total North American grid that can give you an idea of that. Today's electric grid is traditionally a one-way flow of electricity. You have generating stations, transmission lines, distribution lines, taking them to customers, various types of customers, and it's generally bulk generation, mainly natural gas fueled in California. It's controllable generation and predictable loads, and there's limited automation and situational awareness. Now, I want to acknowledge that in the power industry, there has been a lot of work done adding information technology and control systems into the industry. But we are going way beyond with what we're planning for smart grid, what has been there before. Right now, the other big thing is a lack of customer-side data to manage and reduce energy use. And I know Ron Hoffman, who's here today, and Dave Watson know a lot about that side of the equation, working on demand response and how we're going to make automated demand response work into the system. There's lots of customized proprietary systems in that Western grid and then in the Eastern grid, and that really becomes an issue with interoperability, and that's why standards are so important. What I also wanted to say is that traditional electrical power systems consist of many individual elements connected together to form large, complex systems. They're capable of generating, transmitting, and distributing electrical energy over large geographical areas, like I was showing you before. Because of this interconnection of elements, a large variety of dynamic interactions are possible. In the past, the primary concern was the way the power system responds to changing power demand and to various types of disturbances. Power system dynamics are not easy to understand, as it requires a physical understanding of the underlying basic physical laws of electrical engineering. Perhaps the most important and unique feature of an electrical power system is that electrical energy cannot easily and conveniently be stored in large quantities. Now, there's a lot going on in the world of energy storage, but so far we're seeing short-term, I would say relatively short-term, a few hours, of storage possibilities. It's not, and the costs are still being worked out of how that's going to be made cost-effective. And there's a lot of regulatory issues involved, too, that we're dealing with. So what I want to talk about is, at any instant in time, the energy demand has to be met by corresponding generation. Electric grid modernization, or smart grid, will change our grid dynamics and immensely add to its complexity. So modernization electric grid, what is smart grid? I want to tell you all this because I'm trying to give you a reason why I think we need more people from a power engineering perspective looking at all this. The smart grid integrates information technology and advanced communications into the power system and to do many things: increase system efficiency and cost effectiveness, provide customer tools to manage energy use, improve reliability, resiliency, and power quality, and enable use of innovative technologies, including renewables, storage, and electric vehicles, and hopefully reduce our carbon emissions and environmental impact. Now, the warning I want to put out there is that I believe it's especially dangerous for students, researchers, and industry professionals to think of information technology and advanced communications as a panacea that's going to make the electric grid smarter without also understanding and analyzing the physical phenomena of high voltage power system dynamics. These are very different systems than traditionally people would deal with in the information technology world. So why is electric grid modernization important? Well, the National Academy of Engineering hailed the electric power grid as the 20th century's engineering innovation most beneficial to our civilization. A 21st electric system is essential to America and California's ability to lead the world and create jobs in the clean energy economy of the future. And in California, smart grid is needed to support the state's overall energy and sustainability policies, including Governor Brown's goal to install 12,000 megawatts of renewable distributed generation by 2020. This is no small engineering goal. This is a very big, big goal that we have. We have, I think, about 50,000 megawatts peak now, maybe more in California. So 12,000 is a very large percentage of that. And it's going to change the dynamics in ways that we're just traditionally not used to having to deal with. There, I have a picture of a White House framework that was released last June. The title of that was a policy framework for the 21st century grid, enabling our secure energy future. They laid out some key recommendations, enabling cost-effective smart grid investments, unlocking innovation, empowering and informed customers, and securing the grid. Now, to me, those are easy to say, and they're really hard to do. Really, really hard to do. The work that we're doing in standards, the standards work, trying to get standards so that we can have interoperability, so that we can allow the investments to be the most cost-effective. It's very, very challenging, but it's also very rewarding, and that's why I want to get you guys excited about it. In California recently, San Diego Gas and Electric, Southern California Edison, and PG&E developed their first smart grid deployment plans in 2001, as was required by the California legislation, which outlined their grid modernization visions. Some of the smart grid challenges that we're facing, these are just a few, really. There are many, many technical challenges to overcome, particularly in electric reliability and resiliency, power quality, workforce, and public safety. If we really have, just think of it, we really have traditionally always had generation, large generation was the source, and then you just plan for where that's going to go, travel to the customers. And a lot of the power system analysis is based on those assumptions that the electricity is going to be flowing one way. If you have large amounts of distributed renewables, small, all over everywhere, well, basically these are generation sources everywhere. Storage, which looks like a generation source too. Demand response, which is actually going to change the grid dynamics quite a bit. It's completely changing the way we're looking at the power system. Smart grid is going to require additional ratepayer investment, and avoided stranded assets is really critical to think about when we're doing what we're doing. The normal life cycles of power equipment are up to 40 years or longer. So planning this out in a way that's not going to have a huge impact to ratepayers in their wallet is challenging, is extremely challenging. Especially when in the IT world, a lot of times people, well, you know, something can get improved and we'll replace it in a couple years. That's the mentality. We have to be very careful about that. The smart meters that we've deployed in California have 15 to 20-year life cycles that they were, you know, planned on. 15 to 20 years for that kind of intelligent system is, I would say, not the norm that the IT world is used to thinking of. And so some of the other challenges, just coordination. There's so much is going on, even within a state. It's difficult. Our staff, we encourage more information sharing across our utilities and pilot demonstration projects to involve multiple utilities. But there are a lot of challenges. Right now, one of our big challenges is just, as Ron and Dave know, enabling the second radios in the deployed smart meters. There's actually 2 radios in the smart meters. One is to communicate the data back to the utility, but another one is to communicate the data in real time in a low power network, home area network, so that people can get real time energy usage. We're facing many challenges in the standards world to be able to activate those right now, to get that real-time energy usage data available to people. Cybersecurity is becoming increasingly important, you probably have heard, and there's a number of technical and regulatory challenges that we're facing in dealing with it. People are more and more aware that by adding information technology to a power system, that we have to be looking at it from a cyber perspective. But there are a lot of challenges, and there's a lot of work. So that's what I'm trying to get you guys excited about, too. The development and adoption of standards and standard maturity is critical for smart grid. Involvement in standards-related efforts, such as the Smart Grid Interoperability Panel, is often not well coordinated at a state level and runs up against resource constraints. There's so many things involved that could use more and more people. In all the standards work, I think I could pretty much fairly say, I don't know what you guys think, but every standards working group that I've been involved in, they need more people that are related to the smart grid, the power system, particularly more people that really understand from a power system perspective the issues that we're addressing. I can give you one example. Right now, there's work being done at the International Electrotechnical Commission, the IEEE, to develop a common information model. And basically, what it really is a dictionary for all electrical terms that can be used by every IT system out there, so that you know what you're referencing, and that if you communicate with one piece of equipment with another one, it knows what you're talking about. Believe me, getting that common information model fleshed out is not easy, especially because there are a lot of proprietary systems out there. People have already kind of developed some of their own definitions and stuff. These are the challenges that we're facing, and also because unless you have that power system background and experience and understanding, it's hard. What are you talking about with these systems? You need to understand it. So my last point is just that there is basically a lack of adequately skilled workforce, particularly in electric power and energy engineering, who also understand IT and network communications. I'm facing it myself. I mean, I have an electrical and computer engineering degree from UC Davis. I didn't study power systems. I didn't have the opportunity to study power systems. But over the last number of years, I got myself into energy because I saw energy was important. I got myself into electric side, and I've been studying. I took a power system analysis class when I could 10 years ago. I studied enough to get my license in, and I studied on power. But what I've noticed is there's a lack of courses out there for engineers like me and others to even go back and get the power engineering training that we need. So this is what I wanted to bring your awareness about, and to others too. Let me see, where am I going? So here's some examples of jobs. This we just kind of threw together. This is by no means, representative of all the jobs. But I just want to show you there's jobs. There's a lot of jobs in this area. Power systems, smart grid, kind of some traditional power and energy engineering jobs, distribution engineering, electric power systems, energy engineer, energy management engineers, energy storage, all kinds of jobs, system planning, utilities engineer. There's a lot of cybersecurity, but one thing is people really also, it benefits a lot to have an understanding of the power system too when they're working on these cybersecurity issues. One of the things in the cybersecurity world, authentication. They're used to being able to require authentication. Well, if you don't get that authentication, you don't allow somebody into the system. Well, in a critical situation on a grid, you don't want to be shutting out, someone from being able to operate, or you don't want, you have to really be careful when you make those kind of decisions, because it could impact a large part of the power system. There's telecommunications. We're bringing in communications technologies into the grid now in much larger ways than we ever have before, but there's a lot of challenges in doing that. The AMI meters that we have deployed now, as Ron and Dave know, I mean, the networks that they have, there's challenges. We can't get all of that data back to the utility as fast as we might like. Sometimes it's 3, 4, 5 times a day that they're getting it back, and it's just challenges when you have amount of data that we're talking about. Storing all that data, processing all that data, analyzing it, incorporating all, that's more into the information systems issues, and the applications engineers. So these are just kind of, I wanted to show you some examples of all the work that's out there that we need more people. Some issues for the U.S. power engineering profession. I believe we need to enhance and increase the availability of power and energy engineering programs, including advanced smart grid technologies. It would be really nice. I took a power system analysis class 10 years ago. Granger and Stevenson is a classic from 1994 in power system analysis. But it would be really nice to have a completely revised power system analysis book that really, and it might be out there, I'm not sure. I just am not aware of it. But that, and then courses that allow us to integrate the smart grid with what the traditional power system analysis looks at. Transmission and distribution face perhaps some of the biggest challenges related to the smart grid, including the integration of more customer system operation dynamics, as I mentioned before, as well as the integration of large-scale renewables and intermittent resources. One of the challenges with renewables is that it is intermittent. It's not always there. Sometimes you might not see that if you look at it averaged over an hour, but last week, San Diego Gas and Electric, one of their engineers, we had a workshop, and they showed us how if you take that down to the minutes, you can see those fluctuations, and the power system is feeling those fluctuations, So managing all that is a real challenge. Interconnection and synchronism with microgrids, and effective, let me just say about that, probably microgrids are going to be coming more and more. I mean, that's what it seems like makes some sense to me. The challenge is most microgrids, if not all, are going to want to connect to the Western grid or the Eastern grid or the Texas grid. They're going to want to connect. And then they're going to want to be able to support themselves if they need to. But that synchronism, when I showed you that picture before, in the Western grid, all those generators have to be synchronized on the whole Western grid. So the frequency needs to be regulated. I mean, if you come on and off a grid, you have to make sure you're synchronized again with everything else that's on that grid. These are big challenges. Effective integration between field operations and back office information technology systems. There's so much more data that's getting input, coming in. What are we going to do with all these AMI data? There's new systems, new demand, customer information systems, new outage management systems, but integrating all that, and these are challenges we're facing. On operations, there's a lot more new dynamics on the operations, as I mentioned. So how do we enable high penetrations of distributed, intermittent, renewable, clean generators, storage, electric vehicles? I mean, if we really are going towards a massive amount of electric vehicles, I believe it's going to be really, we're going to have to manage it from a grid perspective. I personally question whether or not we can assume we're going to know how people are going to charge their cars and when they're going to charge their cars or where they're going to charge their cars, especially here in America. I just don't know how, that's going to be. So I think we're going to need a lot more smarter, systems to even manage it. How do we integrate? Oh, and then the other note was we want to enhance rather than degrade grid stability, resiliency, power quality, and safety. How do we integrate and use synchrophaser technology, which measures more real-time grid conditions with phaser measurement units for substations and stuff? There's a lot more data, and it's a lot more data. How do we really effectively use all this data? So there's some recent efforts that I wanted to let you know about. The IEEE Power and Energy Society has had a U.S. Power and Energy Engineering Workforce Collaborative. It was an initiative to address concerns about the U.S. Power and Energy Engineering workforce. I want to put this up because it's not just me saying this, basically, too. That the IEEE worked on this, and that collaborative, their main objectives was to strengthen the case for extraordinary efforts to build, enhance, and sustain university power engineering programs. The Workforce or one of the main objectives was to do that. The Workforce Collaborative developed a report in April of 2009 entitled Preparing the U.S. Foundation for Future Electric Energy Systems, a Strong Power and Energy Engineering Workforce is needed, basically. They concluded that skilled power and energy engineers are the foundation to successful design, planning, construction, maintenance, and operation of our nation's future electric energy systems. An ample supply of these engineers is critical to meeting national policy objectives towards energy independence, security, global competitiveness, environmental stewardship, and quality of life. One important recommendation to get that supply was to build, enhance, and sustain the university power engineering programs, in part through increased research. There also was something that came out of that. A scholarship initiative started. That began last year. I had the honor to be asked to be on our Region 6, our Western U.S. Scholarship Committee. And these provide scholarships and real-world experience for undergrads who are interested in power and energy engineering careers. For qualifying students, the program not only provides scholarships, but facilitates internships, co-ops, and many opportunities to get experience in power and energy engineering. The scholarships amounts might not be huge, but they were out there to help. $2,000 the first year, $2,000 the second year, $3,000 the third year, and you have to continue to qualify. Region 6, we received 42 applications, and we awarded 20 scholarships in the fall. Only 3 of those were from California, and none of them were from University of California. And that's what I'm here to tell you. Like, I really want UC engineering students to be aware of what's going on and how, we need you to be a part of this. One requirement for the scholars is to be enrolled in an undergraduate electrical engineering program that offers a number of electrical power engineering courses. So hopefully we can get that going, at some of our UC campuses. That's my dream. This is some information about the standards and interoperability work that we've been doing. Interoperability is going to really be key to enabling us to reach a lot of the goals that we have. And it's not an easy journey. There's so many diverse systems and components, and getting them to work together, integrating them, having the two-way communication among all these interconnected elements, it's a big challenge. So at the national level, there is a lot of great work going on with smart grid standards, particularly by the National Institute of Standards and Technology and the Institute of Electrical and Electronics Engineers. The NIST has a smart grid interoperability panel, which is an organization that's a public-private partnership, and anyone can get involved. It's really been a way for me to get connected with professionals in this industry that I never would have had before. There's lots of virtual meetings, so you don't have to travel. There are opportunities to travel too, but I have learned an immense amount from that. And so I wanted to let you guys know. This is the conceptual smart grid model that they have, that NIST uses. So you just kind of shows the complexities in a way, in a different way, but bulk generation, transmission, distribution, customer, and then you have market systems and the operations and then other service providers. There's some discussion of whether or not we need a new domain, distributed energy resources domain, because it changes the whole dynamics of the system so much. And this is a kind of a further example going down deeper into just the distribution side. So I just wanted to throw it up there to show you some things. The GWAC stack, the GridWise Architecture, has come up with this layered GWAC stack, and I think it's similar to like the OSI model out there, a 7-layer model I've heard. One of the things I want to point out is that network interoperability is really key in one of, in one of these lower layers. The bottom layer is actually the physical wires or the wireless connection, the systems that allow the communications. But up here on the top, this economic regulatory policy drivers, these are the things that are going to drive where the requirements are, how the requirements are developed, and how effective they are. There's a lot of focus on the economic drivers because a lot of people in the industry, that's what they're interested in. I would love to see, we're getting more focus on the regulatory drivers, but it's a big challenge and it's a lot of work. And there's a lot of opportunity to get involved in that. This I just want to throw up there to just say, this is like what we affectionately call the spaghetti diagram, and it kind of just shows you the complexity. These are like subsystems in the power system. The pink is bulk generation, that's plant control systems. The green is transmission-related systems, phasor measurement units, transmission remote terminal units, transmission intelligent electronic devices. There's operations is a huge, that's the yellow, so operations is all over everything, outage management systems, SCADA, which is the supervisory control and distribution system, which is a very intelligent system that the industry has had for a number of decades, but it's completely getting, it's getting revised with everything else that's going in smart grid. So there's just a lot, and all these spaghetti lines are the interfaces between all of these, how they have to communicate data between each other, and it just gives you an idea of the complexity. So, how can the University of California help make a smarter grid? Well, I hope I've made the case today that there is an urgent need for adequately trained electrical power and energy engineers in both traditional power engineering and information technology communications. And it's not an easy feat. I mean, I'm not saying it's an easy feat, but this is just, it's what we're needing. There's an urgent need for programs that revamp the traditional power and energy engineering courses that are out there to integrate what we're doing now in smart grid. There's an opportunity, this is my personal thing. I really think there's an opportunity for the University of California to fulfill an important role to provide a holistic power and energy systems engineering program and vision to solve the industry challenges and cost effectively build California's 21st electric power grid. The power and energy engineers work with some of today's most exciting technologies, developing solutions to problems that affect our lives and our lifestyles. So with that, I wanted to close up. This is a quote from, and thank you very much for letting me be here. This is a quote from our president, Mike Peavy. Smart grid is a foundation for the transformation of the electric industry from a passive and reactive system to one that is more reliable, efficient, and cost-effective for consumers. By using more advanced technologies, a smart grid will empower consumers to manage their electricity use and save money, help utilities reliably deliver power, and increase our use of renewable resources. Please feel free to contact me. I'm hoping to hire one of your mechanical engineering students as an intern here soon. So we're really trying to get more connected with the universities. Lastly, I'm putting this up. This is in memory of two friends of mine and colleagues, Don Smith and Kirk Brott, who I miss very much. They passed away in 2010, and these were two of our power engineers who really understood that they understood things that I didn't understand, and they helped mentor me in many ways. And I miss them. So I just wanted to say this is in memory of them. Thank you.
Okay, questions?
Yes, I was particular question about the hierarchical structure of grid. If you have a super grid, you want subgrids and maybe microgrids there, where each of those subgrids can operate alone or put power in and take power out. And this is a technical problem, but it's much more an institutional problem. Right, because essentially we built a whole lot of hundreds of megawatt turbo generators and then gas turbines turning on tens, and now if the World Alliance for Distributed Energy does, there'll be megawatt turbo generators. So the actual technology underlying this changes, yet the institutions, the utilities that make up this whole system don't change as rapidly.
I even have thought about going back to Thomas Edison when he was, when he lost out, I should say, in the War of Currents. AC won out over DC a lot because AC was better for long distances. Well, if we're really talking about distributed generation and stuff, and then we have a lot of our equipment that we use, at least in our households, that uses DC. Maybe we should be rethinking, what voltages we should be doing that. Should we go DC to AC and AC back to DC? Or should we just go DC to DC and add a lower voltage? I don't know. I mean, these are big questions that I agree that the way the systems are set up now, it may not. That's why I think it's so important for universities to get involved in these kind of questions and working on these kind of solutions. So.
Yeah. In Texas, the commission ruled that the signal, that all the data that comes out of smart meters belong to the customer, which opened the door for a lot of third-party aggregators, entrepreneurs that are really facilitating the load participation. So what is the California Commission doing to democratize the smart grid in this fashion?
I don't have an answer for you. I mean, I've focused more on the distribution engineering issues. I'm aware of many of the issues in the AMI and the third party, but I really don't have an answer for you. But I can definitely get you in touch with somebody that hopefully could answer that. I think the key